that is got to equal the summation over n of Cn e to the minus I En t over h bar. And then I believe this stuff is just psi n of x. Oh, and so psi m of x, and then times psi n of x. So here's this stuff is just psi n of x, right? So now I'm going to multiply both sides by psi m of x. Okay, and I'm almost done, so give me another minute or two. All right, now watch. If I integrate both sides over dx, so if I integrate this over dx, so I integrate this over dx. And over here, I'm left with the integral of psi general of x and t of psi m of x dx. And what's this going to equal over here?
This pull the summation and b out of the integral.
So you can bring the integral inside here, but what does the integral, what's the only condition that the integral survives? So this becomes the integral of the summation over n of Cn e to the, well this becomes the summation over Cn e to the minus I En t over h bar times what? The integral of psi n dx, but that's like I hat j hat. So that's the Kronecker delta, right? So that becomes the Kronecker delta of psi m n. And so when you sum over n, what's the only thing that this survives for?
M equals m.
For n equals m. So so how many terms in this summation survive? One. So this pulls out essentially Cm. Right, we're going to say that Cm e to the minus I Em t over h bar. Alright, so what I'm left with over here is the integral of psi g of x and t, psi m of dx dt. So psi g x of t, psi m of x dx equals Cm e to the minus I Em t over h bar. Alright? Now, Griffiths also goes to show shows that the Cm's are not an f of time. So they're constants. So therefore, this equation must be true at t equals 0. Right? And therefore, if we put in a t equals 0, we find the integral of psi general of x comma 0, so t equals 0, of psi m of x dx has to equal Cm. And if you want, you can change all the m's to n because that's a dummy variable, so Cn, so that's Cn. And so this is left to find Cn. So I didn't quite finish where I want to go. I want to finish, so this is the end of the formalism. But now, this is exactly where example problem 2.2 takes off. Sample problem 2.2, and this is what you must do for next Tuesday. All right, must do this. What happens is 2.2 gives you, so 2.2, example 2.2 says you have infinite 1D wells. All right? The solution to h bar h0 psi equals ih partial psi with respect to t equals this thing. Right? That's what we just got. It says find psi general of x and t or psi general of x comma t equals 0 equals ax times a minus x. Okay, so what it does is it says this. I want to find the total time-dependent solution to Schrodinger's equation. And I know it looks like this. It's got to be some expansion of this. Right? So to find this specific the particular solution to this, I have to find the CNs. So how can I find the CNs? Well, I'm given that I know at time equals 0 the wave function. I put the wave function in this condition. So therefore, if I put the wave function and its time equals 0 in here, I will be able to solve for the CNs. And then once I have the CNs, do I have the solution for the full time-dependent Schrodinger's equation?
Yes. Yeah, it's like a Fourier transform.
Yeah, it's like a Fourier. In a sense, this is all language of Fourier because it's an infinite basis set. Okay, guys, we made it through the whole formulas. If you can get through this, this is what we do from here on in. And this is all we do. And then when you solve the hydrogen atom, you just solve the hydrogen atom and do this. So this is it. This was a big class today. All right, and I know it was messy, and there's a lot of tangents because you just can't do things. I do a lot of steps in between those tangents. All right, but what you guys have got to go through is really nail this formalism and this procedure. And trust me, guys, if you can do it, if you can follow this beginning to end, and then do the example 2.2, you're golden.
What did you do?
What's that?
Let's do it.
So here's what I'm going to ask you for Tuesday. I'm going to ask you to do that example problem, all right? But I'm not going to ask you to handle it in. It's example problem 2.2. But what I will ask you to hand in is the problem 2.7. Problem 2.7 is essentially problem 2.2. It just gives you a different starting condition.
I think I started problem 2.7. It was very similar to what you did in class today.
So that's what I'm saying. Everything we're doing is exactly it. So 2.7, you don't have to do anything. You can start right here.
Yeah, that makes more sense.
Yeah, 2.7, you can just start right here and then just go right here. So here's problem 2.7. Write down this, write down the new conditions, put it in here, find the integral, find the CNs, and you're done.
It's a fun integral.
Okay? But the important thing is simply not to be able to just do it. It's to see how this whole formalism developed. All right? If you see how the whole formalism developed, great. And I know I say infinitely dimensioned function space a whole lot, but is that the key to this? And the answer is yeah. Okay? All right, thanks guys for taking a little bit longer, but we'll get you through those problems.